Hello, Neuromatch4, and welcome to my presentation on automated neuron tracking in freely moving C. elegans. So, a quick introduction on the history of C. elegans and neuronal imaging. So in the Zimmer lab, we've done a lot of work on immobilized animals and extracted traces from these beautiful videos, as you can see in this image right here. We get beautiful, beautiful patterns of activity that are very coherent across many neurons and across time. We can even interpret those patterns of activity as fictional behaviors because of the well-known names of the neurons and the behaviors that those neurons themselves are associated with. However, of course, what we really want to do is the next challenge, which is to image these neurons as the worm is actually doing these behaviors, not just fictionally thinking about doing these behaviors. So we would love to see maybe some similar structure or maybe quite different structure in these same well-known neurons as the neuron is moving around in an unrestrained environment. However, there are lots of major challenges with doing this. I've got a couple right here. In particular, there's a lot of motion between images, a lot more motion than your average object tracking task like pedestrian tracking or some other classical machine learning task. Neighboring objects, that is the neurons, look very, very similar. And there can be quite dramatic non-rigid deformations of these objects. They're not rigid, they're not just spheres, they're actually moving and squishing across time. So I'm super excited to talk about the computational solutions that we have for this challenging problem, and begin with a lot of the wonderful, wonderful tools that have been published already in the neuron analysis community. And specifically, we start by segmenting and detecting our neurons using a trained version of Stardist, which you can see here works quite well for neurons and separating them from both their neighbors and from background. Then we combine each of these across time into something we call tracklets, because these are short time tracks that would accumulate errors across time, so they're short. Thus, they're called tracklets. And in more detail, we have our nice volumetric image right here. We can see these individual neurons, and these are connected to their positions in the next frame. As we can see by the blue dots, which are the neurons that I will show you in one moment. But in principle, these tracks will accumulate errors, as you can see here, and so they're only stable for a short period of time, which could be some seconds or could be a couple minutes for some relatively easy or more isolated and trackable neurons. So we can see that in the next frame, many of the neurons have moved to their partners and are successfully tracked. And then we can create our beautiful tracklets from this. All right, but this is not enough, of course, to track an entire video. So we are going to do the classic strategy of concatenating or stitching these tracklets into the full track using a different method, which is going to be a sparse global tracking method. And this allows us to stitch the tracklets together, and then I've built a GUI in Nepari for manual finalization of both the tracks and the segmentation. And I wanted the climax of this talk to actually be a live demo of the GUI itself, but unfortunately the network is down at the University of Vienna, so I cannot show you that. But you can see here that we have our segmentations around the neurons. And here is a particular neuron and the Z coordinate of the centroid across time. And we can see in the different colors how our different tracklets are stitched together. For the most part, very long, although some behaviors cause difficulties in the tracking. In particular, the reversals in gray can cause some differences in position. We can see a systematic difference in Z, for example. But the turns in particular cause massive deformations and huge difficulties with tracking. And so many tracklets are destroyed at that point in time. Okay, wonderful. So a fully automated output of this pipeline, a subset of the neurons that I'm going to show you, is as follows. So we can see some activity that is associated with certain behaviors and across multiple neurons. So for example, this increase in the white forwards and decrease in the gray reversals, and vice versa, increase in reversals and decrease in white forwards, and some more complex behavior as well. Now this is the automated output, which has a lot of gaps, obviously, but on the next slide I can show you a manually filled in and curated version of some of these neurons. So this is not a finished data set, but it does fill in many of the gaps that we saw on the previous slide. And we're very, very excited to analyze these data, and I don't have anything extra to say about that at the moment, but please ask me any questions in the live session. All right, thank you all so much for listening, and thank you also to the VIP2 program and the Vienna Biocenter for funding.